Do you all see my screen? Okay, thank you. So our paper was on NOMA in the context of non-terrestrial network. It was led by Dr. Baha Dean Yusuf Belmakki, who used to be a postdoc in my group and who's now an assistant professor in Heriot University in Edinburgh, Scotland. So when we talk about non-terrestrial network, obviously we are talking about a variety of platforms, starting from satellites, of course, at the space. And with satellite, we have the LEO, MEO, and GEO families. These are operating at different altitude. We have also platform operating in the stratosphere in the near space, known as HAPS. They come in different form and shapes, gliders, airships, and balloons. But NTN also includes low altitude platforms in the form of drones or tethered balloon or tether network tether flying platforms. So the drone will be operating in the few 100-meter altitude, while this tethered platform may be operating in few 100-meter all the way to a couple of kilometer altitude. Now, often non-terrestrial network are related to some challenges. So spectrum efficiency can be one. The fact that they have to deal with many users because they tend to be actually operating from a high altitude. So even if the dense population is relatively low, they will have eventually to deal with many users. Latency is an important criteria of selection of the right platform. That's one of the advantages of LEO compared to GEO because they are much closer to Earth, so that reduces latency, and some of the applications that are not suitable for GEO are enabled by LEO and anything below. We need also to pay attention to fairness, and of course we want this network to be scalable. So in this context, we looked at NOMA. How can NOMA be used in conjunction with these non-terrestrial frameworks? So I will not repeat what Hamid and Edward presented, but NOMA is a perfect or an ideal type of multiple access scheme to basically convey information to multiple users simultaneously using the concept of superimposition coding and successive interference cancellations. So in the context of non-terrestrial network, both, let's say, uplink and downlink, this can be adopted. So in this case, on your left hand side, we see downlink scenarios where a drone acting as a base station is sending in a NOMA fashion two signals to two users with different power allocation. And as Hamid explained, one can use the NOMA concept and successive interference cancellation with superimposed coding to decode the two messages. What I would like to highlight is that often we need to power allocation, and the power allocation can be done based on few strategies. What I would like to mention here is the so-called CSI-based strategy, where basically we'll allocate power based on the channel quality or how good is the channel. But also one can use a quality of service based strategy where basically more power is allocated, let's say, to user to whom we would like to give a higher priority. So these can be strategies we use to allocate power in a normal context. So in our paper, as you know, when we write a paper for Proceedings of IEEE, it's supposed to be a survey high-level paper. So we first of all try to convey to the readers that actually NTN with NOMA can address many of the challenges that NTN without NOMA face, from a massive connectivity, latency, fairness aspect. That was one of the aspects we tried to convey in one of the sections. But then we went into the different interaction with emerging technologies, NOMA and NTN. So we looked at three aspects. We looked at extreme frequencies, we looked at RIS, and we looked at ISAC. So let me go a little bit in detail into that. So when you talk about the interplay between NTN, NOMA, and extreme frequencies, is how we can use these three technologies together. So often when we think about NOMA, we think only from an access perspective, which is shown on the right-hand side of my slide, which is the standard application of a multiple access scheme where we have multiple users trying to access, like information in a simultaneous fashion. That's of course a perfect application of NOMA or any other multiple access scheme. But actually, in the context of NTN, we may need also to have NOMA for backhauling. So for instance, here on the upper left corner, what we are showing situation where we have one ground station trying to communicate with multiple hubs. So in this case, we may use NOMA to give access to these two flying platforms from the same ground station. So you can also have, or you may have also the need to create backhaul link between, let's say, aerial platforms. So in other words, if you want to multiplex, let's say, a ground backhaul with a backhaul to hubs or to tethered flying platforms. So in this case, again, we are using NOMA in a backhaul setup, not in a multiple access, and this is also a useful scenario. The second, as I mentioned, interplay we looked at is how we can combine IRS. IRS has been very popular over the last 10 years or so. And can IRS be used in the context of non-terrestrial network? Of course, a lot of people have looked at this problem. And when you look at RIS in the context of non-terrestrial network, we have two scenarios. We have the TRIS, which are the terrestrial RIS that are aiding a non-terrestrial network-based network, but we have also the aerial RIS, the ARIS, where the RIS is attached to one flying platform. So let's take, I mean, there are many scenarios shown in this graph. We can take one very basic one. You have a drone basically acting as a base station. It doesn't have a good line of sight with these two users. It takes advantage from RIS attached to a particular building, and with that, it's able to basically connect to these two users. So that's kind of an example where an RIS is used in the ground. Now, on the right-hand side, just to illustrate one of the examples we are showing here, let's look at this example. We have a base station on the ground, doesn't have direct line of sight with these two users. We have a drone that happens to have good line of sight condition with both the base station and these two users. The RIS is attached to this drone, and the RIS is allowing to create this virtual non-line of sight or virtual line of sight connection between the base station and these two users. And of course, NOMA can be used to multiplex these two users. And there are many other examples illustrated here showing different kind of network configuration where basically RIS can be helping situation where basically there is no line of sight between transmitter and receiver. And then the RIS can be either put on the ground or attached to one of these flying platforms. As I mentioned, the third aspect where NOMA can be used with non-terrestrial network and an emerging technology is ISAC. As you know, ISAC is a technology that has been researched quite a bit, but by our colleagues and in our community. And in the context of ISAC, basically you can not only multiplex two standard signals, but actually you can choose to multiplex one signal that is only for communication and the other for sensing. And in this case, it can be done for both downlink or uplink. And in this case, of course, when you use communication, you will need to basically use success matrix cancellation to get your particular desired signal. But sensing can be just there to basically give you information about the sensing target, user 1 or user 2. Now, one other aspect we covered in the paper is different kind of architecture using NOMA. So we can have the classical so-called cellular architecture, where typically a base station will be attached to a drone or to a HAPS, either in a direct to a drone or HAPS to users, and with that you can use again NOMA, or in a relay fashion. So where basically you have a base station connect to the basically background internet network, not having direct line of sight with users, and then you create this or you can rely on this drone that is relaying information and multiplexing information using NOMA. So that's what I would call cellular configuration. We may have an integrated access backhaul where basically you have, let's say, inter-satellite or inter-aerial link satellite to HAPS, HAPS to HAPS link in the space or in the air. But then eventually you have, these typically are backhaul links, but eventually you want to have access given to either ground user or aerial user, And in that case, you have the access aspect. So, and that's why these are typically called integrated access backhaul, like it is done in terrestrial network, but here it's done in a non-terrestrial fashion. You can have ad hoc network where basically you have self-organized basically base station and user configuring themselves in a way that transmitter and receiver are communicating typically via a drone, or perhaps if it is kind of a larger network. And again, NOMA can be used in the context of multiplexing multiple users. And eventually, like we talk about cell-free in the context of terrestrial network, where we have basically low complexity, let's say, access point distributed in different distributed base station. You can replicate that in non-terrestrial fashion. For example, satellite acting as a CPU, and you have different access point on the top of hubs, and the hubs can distribute information to users either on the ground or aerial user for drones, basically like eVTOLs or drone for delivery of merchandise. So what are the applications of non-terrestrial network with multiple access? Obviously, global connectivity is one of the main aspects, connected and unconnected, connecting people in rural, hard to reach areas, but also in urban environment, as you may have seen, there is quite a bit of activity on the so-called low altitude economy. We are talking here about delivery drones, flying taxis. These will need to be connected, and non-terrestrial network can be a very good solution to connect such kind of new infrastructure or this 3D network, in the sense that we'll have user on the ground, but also user operating at few hundred-meter altitude. But also vehicular network may benefit quite a bit from non-terrestrial network, given the obstruction that can be observed in ultra-dense, basically metropolitan areas. As an example, we are trying to illustrate here the benefits of non-terrestrial network. So let's consider here a flying, a tether balloon, okay, acting as a relay. So this is like an ad hoc configuration using the terminology I presented earlier. So you have a source trying to communicate to these users via a relay, and this relay happens to be, let's say, a tether balloon operate at a few hundred meters, let's say 800-meter altitude. In this context, we assume that you have ground user, but you have also these UAV users or eVTOLs. The way these have been modeled, the UAV have been modeled as a binomial point process. On the other hand, the vehicle on the road have been kind of modeled using this Cox point process for lines, because we assume that they are on the roads. So you have a signal originate from the source, multiplexing two NOMA basically information bearing signals, relay, decode, and forward, retransmit these two information via NOMA again to these two users. And in our analysis, we assume that we use a quality of service-based power allocation, where user of category 1, let's say, are users who require low data rate, less than 1 bit per second, but have a high priority, emergency message being a perfect example for that. And then you have user 2 or the user 2 type who are higher priority, lower priority, but require high data rate, let's say more than 1 bit per second. We showed comparing an OMA and NOMA strategy in our paper that basically for if you focus on the first type of user, the kind of high priority low data rate, NOMA will always outperform for an out probability an OMA strategy. And also for the low, if you look at the low priority but high data rate, those who are more than 1 gigabit per second, again, you see that the NOMA, the solid line, outperform NOMA. So, that's kind of a nice outcome of this analysis, illustrating the benefit of NOMA for both category of users. And we went further to show in a different configuration the advantage of non-terrestrial network versus terrestrial network, especially in dense urban environment. So we looked at two scenarios, a scenario where, again, we are trying to communicate from this, let's say this source to this user via a relay. But let's assume that the source can be either this non-terrestrial basically flying platform at few hundred meters with very nice line of sight type of condition, in comparison to basically an RSU or a roadside unit, which is at the ground, pretty much at the ground level. And clearly, having a source at a high altitude with very good line of sight condition gives you much better basically end-to-end performance when you do the two-hop type of analysis compared to a source that is on the roadside at a regular altitude, because of the obstruction that you can see, especially in metropolitan environment, and because of the extra beamforming capability that we assume in our source that minimize interference coming both from the ground user and the UAVs. So in short, this is a little bit a summary of our paper. We also mentioned some of the challenges that we experience in non-terrestrial network configuration, the difficulty of sometimes of estimating rapidly varying chance, in particular for LEO constellation on high-speed orbit, the hardware payload that have to be customized. Not everything that work on the ground would work at high altitude. I mean, for drones and tether balloon, we are still at tens or hundreds of meters. That's okay. As soon as you start over the stratosphere, HAPS, or space like satellites, you have to pay attention to basically a payload that is operating at low temperature, at low pressure. Sometimes the weight and the size of the device matter, because swap constraints are very important for HAPS and satellite. The weight counts a lot in the energy budget of these flying platforms. So you need some time to adapt things that have been designed for ground operation, where these constraints are often not that important. Security, especially in the context of NOMA, where you're multiplexing multiple users. If you need eavesdropper, especially in non-terrestrial network, where you can have a nice line of sight, so you can have jamming application, you can have eavesdropping that eavesdrop on the whole network, because you're able to listen to all the users. These are some of the challenges that we highlighted. And the direction, where do we see non-terrestrial network and NOMA going? We think OTFS, although we all know that OTFS will probably not be part of 6G, but beyond 6G, if we look at super high mobility type of units, this can become an important aspect that will be researched. Full duplex capabilities to maximize or double spectral efficiency, and also doing more experimental trials that tend to be expensive and challenging because you have to operate in the air or in the space. Thank you for your attention, and we also want to publicize some of our works by looking at some of our channels, and I will be happy to take some questions during the Q&A part of the webinar. Thank you.